So let's just remind ourselves of this. So the ability of a force to cause rotation. Now let's look at a few examples of this. So I'm just going to use a thicker pen. So let's say I've got a long rod over there, and this rod is fixed with some sort of ball joint to the wall, so it can move in any direction I want it to. And let's just get a system of axes going. So it's fixed to a wall like so. And let's say at this point we construct a y-axis upwards, an x-axis to this side, and we've got the z-axis coming out of this page. So you have to think in 3 dimensions, x, y, and z-axis over there. So let's say we decide to apply a force purely along the y-axis. So I now apply a force over there, purely along the y-axis. So obviously if this thing is pivoted at the wall and I apply this force, I can expect rotation in this plane. So I expect this rod to rotate in that plane. So this rod will rotate. If I apply the force like that, this rod will sweep out an angle in the xy plane. Now we can look, I can redraw the system, but let's do it for a slightly different force. So here's the wall again. There's our ball joint. Here is a rod. Again, I construct my system of axes. There's Z, there is X, there is Y. And now I don't apply a force that's perpendicular to the rod parallel to the y-axis. I apply a force at some angle with respect to the x and y-axis, still in the xy plane though. So I'm applying a force, say, in this direction. Same magnitude as that, but it now makes this angle theta with the x-axis. This force is still in the xy plane. So remember we said this ability of a force to cause rotation, it depends on 3 things. It depends on how far we are away from the pivot point, how big the force is, and the direction between this rod and the force. So here we can break this force up into a y component, like so. So that will be Fy, and it will have an x component over there. And if this is a pivot point, the x component just pulls against that. There's a normal force pulling back. So this component is wasted if we want rotation. Because it's just pulling straight across from the pivot. The y component, this is the component that causes rotation. So, which of these 2 forces has got the greater ability to rotate? Well, if these 2 have the same magnitude, then the one where the entire force is applied in a direction perpendicular to the rod, that gives me a very good ability to rotate the rod. This one, only a part of the force, the y component, plays a rod rotation, so it's got a slightly smaller ability to rotate this rod. So we will say this has got a large ability to cause rotation. this has a smaller ability to cause rotation. And if this force was entirely along the x-axis, it would have zero ability to cause rotation. Now there's a very nice graphical way that we can figure out, just from this type of drawing, what the ability to cause rotation is going to be. If I redraw this, so just in a slightly simpler form, this was our rod. Let's say it had a length r. This was our force F, and our axis, that's y. The y-axis is over there, x-axis is over there, z-axis comes out. So we said the ability to cause rotation, we call this the torque, and this, the mathematical expression we had for this is it's the magnitude of F, so F is a vector, the magnitude of R being the vector from the pivot point to the point of application of the force, times the sine of theta, where theta is the angle between R, it's the forward direction of R, and the forward direction of F. So in this case, this will be 90 degrees. So this is just equals to the magnitude of the force, in this case, times the magnitude of R. Now that looks a lot like an area. So if I were to draw this area in here, this area has got magnitude F times magnitude R. So this area is equals to the magnitude of the torque. So the area defined by the force and this distance from the pivot point to where the force is applied, that rectangular area is a measure of the ability of this force to cause rotation. The same applies to our second drawing, but here we had, here's our rod. Again, it's a distance r to where the force is applied. Now the force is applied at some angle theta. So what I'm saying is that this area, so if I look at the y component, so the y component will be slightly smaller like that. If I look at the area made by the y component and r, this area will give me an idea of the torque. Does this make sense? I'm saying the magnitude of the torque is equals to the magnitude of the y component times the magnitude of r. The magnitude of the y component is just F, okay, we can put in the r over there, sine theta. So F sine theta gives me the y component, r is just that. So we find every time that this area, so the area defined by the component of the force perpendicular to r, and r itself gives me the magnitude of the torque, of the ability of this force to cause rotation. So the more flat this force becomes, the smaller that angle becomes, the flatter this area becomes, the less of the torque, so the less of the ability to cause rotation. Okay, so that's a very nice graphical way to visualize torque. Think of an area formed by a component perpendicular to a rod and the distance between the pivot and the point of application. But that's only half of it, or that this is okay if you are interested in magnitudes of torque. But we are interested in more than that, because we feel that a rotation that causes something to rotate, say, around the y-axis is different from a rotation that causes something to rotate around the x-axis, say. So we still need to figure out, well, if I really want to characterize torque uniquely, I must take into account the type of rotation I get. So in which plane does it happen, or around which axis does it happen? And I need to figure out then how to differentiate between different torques associated with different forms of rotation. And we can use this idea of this area as a very efficient tool to do that. So consider the following. So let's stick with this idea of a rod pivoted against the wall. So there's the wall, here's a ball joint. There's our rod. And in one case, I will apply a force along the positive y direction. So remember, this is the y-axis, that's the x-axis, this is the z-axis. And in the second example, I'm going to exactly the same rod. So this has got a length r, this has got a length r. Here's my y-axis, my x-axis, my z-axis. And let's say now I'm applying a force in the negative z direction. So this force is pointing into the page. So let's look at the torques associated with this. So we can complete this area. So here we've got an area in the xy plane. And it's the size of this area gives me the torque associated with F. Here we've got an area like so. So this is in the ZX plane, and its magnitude is also equal to the torque of this force. So the only thing that's different between these two pictures is the direction of the force. Here the force is in the positive y direction, here the force is in the negative z direction. Now we know this force will cause rotation in the xy plane. So this rod will rotate upwards like that. Or we can say this is also equivalent to rotation around the z-axis. So the z-axis sticking out of the page. So if this thing is rotating in the plane of the page, it's as if I've pinned it down with something parallel to the z-axis, and it's rotating around that pin. Here we've got rotation in the zx plane. So it will rotate into the page, or alternatively we can say this is rotation around the y-axis. Now, we want to distinguish between these two things: same force, same magnitude of torque, but two different sorts of rotations. And this rotation has obviously got to do with the direction of the force and the initial position of the rod. So we want to figure out, we want to be able to differentiate between these two rotations. So if you look at this picture, it comes down to, I want to find a simple way to tell us that this area has got a different orientation than that area. This area lies in a different plane than that area. So there are, I guess, a few ways that you could do this, but the simplest one is as follows. And you will also learn this in mathematics. It's a very nice way to define an area. Is to define this area, I associate with it a vector that is everywhere perpendicular to the area. So if this area is in the xy plane, anything perpendicular to it can point out of the page or into the page. So let's choose out of the page. So this vector is everywhere perpendicular to this plane, and I give this vector a magnitude equals to the magnitude of the torque. And for this area, I do the same. I take a vector that's everywhere perpendicular to the plane. So just to give you an idea, this vector points in positive z direction. This vector will have the magnitude of the area, but it points in a direction perpendicular to it, so this points in the y direction. And now I can distinguish between these two areas. One has got we call this thing an area vector or a plane vector. This vector that we give, we construct it so it's always perpendicular to the area, but its magnitude is equal to the size of the area itself. That vector points along the y direction, for this one it points along the z direction. So if I look at these normal vectors, or these vectors perpendicular to these surfaces, I can easily distinguish a surface that points from this, it's oriented like that, or a surface that's oriented like that. So it's a very nice mathematical tool with which I can, with one single vector, describe the orientation of an entire plane. Now, this becomes especially useful in the following case. Let's say, again, we've got our rod, the ball joint, and we apply a force along the y direction, and we apply an equal but opposite force in the negative y direction. Right, so one force is trying to rotate it in that direction, the other force is trying to rotate it in that direction. And intuitively we know if these two forces are equal in magnitude, they've got the same angle with respect to this rod, both 90 degrees, and at the same distance away, we expect the thing to be in equilibrium. We don't expect any net rotation. So the torque from this force and the torque from that force must cancel each other out. So we can characterize the torque now from this force by looking at this area. So let's call this F1, F2, and we've got that the magnitude of F1 is equal to the magnitude of F2. So this area gives me the torque from 1. And let's also plug in this direction to tell us the orientation of this area. So I must construct a vector that is perpendicular everywhere, like so, and it's got the magnitude of that torque. For this force, this will produce a rotation in the opposite direction. So the magnitude of the torque associated with this force is given by this area, but because it's in the opposite direction, I decide this plane, it's like I flipped it over like that. So here I construct a vector that points to the back, that is everywhere perpendicular to that surface. So this will be the torque associated with force 1, that will be the torque associated with force 2. This one points along the positive z direction, this one points along the negative z direction. So if I want to figure out now what the resultant torque is going to be, I can just add these two vectors together. So I can say the resultant torque is going to be the vector T1 plus the vector T2, but T1 points in the opposite direction than T2, so they point in opposite directions. So the two will, so this will be equals to the negative of that, or that will be equals to the negative of this, and we get the resultant 0. So if we decide to define the orientations of these planes in this way, with the vector perpendicular to the plane everywhere, then immediately we get a very nice way which we can add together the torques like we would do with regular vectors. Previously I said, okay, let's just say things that rotate clockwise, to that we associate positive torques, to things that rotate counterclockwise we associate negative torques, and then you add them together. This is much more general, because you now get a vector associated with the torque. If these two vectors are anti-parallel, you can add them up and you might get 0 of the resultant vector in one of these directions. But you can now add up torques like this in the top line to give you some sort of resultant vector, which will give you an idea of the resultant torque. So in adding this little extra when we define torques, so by making it a vector, and specifically we make it a vector that's perpendicular to both the force and the rod itself, we can actually work with torques quite nicely. And this operation, if you think about it, we've got two vectors, so the force vector and the position towards its point of application. So the recipe that we have to follow we must take two vectors, in this case the vector f and the vector r, and construct a third vector with a magnitude equals to that times sine theta, and this third vector must be perpendicular to both f and r. So this is what we've done here to define torque completely. We took two vectors, f and the distance to its point of application, and we constructed a third vector that was perpendicular to both of these and had this magnitude. Right, so that's the recipe now for getting torques out and getting a torque vector. And the shorthand for all of this is just we take the cross product of r with f. So this recipe in English is what the cross product means. So every time you see a cross product, you say, okay, I must construct a third vector combining r and f. The vector I can construct must be perpendicular to both of them and must have this magnitude. You can do it for other vectors as well. So for example, let's look at the cross product between the unit vector along the x-axis and the unit vector along the y-axis. And let's think about our recipe. We must construct a vector with the magnitude of this times the magnitude of that times the sine of the angle between them. So I has got magnitude 1, j has got magnitude 1, sine 90 degrees, because the angle between I and j is 90 degrees, and this vector must be perpendicular to both I and j. So if I points in that direction, j points in that direction, the only options we've really got is either something pointing out of the page or something pointing into the page. Now, we've got freedom to choose this, and as long as we're consistent, everything will work out. But the choice we make is to say, well, let's choose this then to be k. We could have chosen it to be minus k, but in mathematics, we usually choose k, and this is just known then as a right-handed coordinate system. If you were to choose minus k, you were working in what's called a left-handed coordinate system. Why is it called right-handed? If you take a right hand and you curl your fingers from I to j, your thumb sticks out of the screen, which gives a direction k. If you did it the other way around, if you chose the left-handed system, curling from I to j, your thumb would into the board, that would give you minus k. So we choose to work with a right-handed system. So what we get is that the cross product between I and j is equals to k. In exactly the same way, you can go and figure out that k times I must be equals to j, and that j times k must be equals to I. So the cross product gives us a very nice relationship between the three principal axes we use in the right-handed coordinate system as well. Right, and this is now the idea or the motivation behind why we bothered with this cross product, because for things like torques, it gives us really all the information we need to describe a system.